Hello everyone, so this is going to be a GCSE Combined Science Trilogy past paper walkthrough. This is Physics Paper 2 Foundation Tier, and this was the paper sat in June 2022. Okay, so I'm going to go through it, model it, how I would have tackled it, and I'll put the Cognito links to the various topics if you need to go back and revise that topic. So question 1 then, these are the different types, there are different types of electromagnetic waves. What do all electromagnetic waves transfer? Well, you should know that all waves in general transfer. The definition of a wave is that it transfers energy and information, but does not transfer any matter. So it's not charge, it is energy, it's not matter, and it's not sound. Okay, so the key thing is waves, like waves coming from your mobile phone, transfer energy and information. Question 1.2, complete the sentence using the words in the box. So different types of electromagnetic waves have different blank and different blank. So what you should remember about the electromagnetic spectrum is that it's a series of transverse waves. Some waves have short wavelengths, some waves have long wavelengths. So you can have one part of the spectrum that has a long wavelength. So one difference is that they would have a different wavelength. It doesn't matter which order you put these in, but because their wavelength is also different, the amount of waves you've got in a certain amount of time is also different. So they also have a different frequency. So my wave at the top, I would say, has a long wavelength and a low frequency. But my wave here has a short wavelength with a high frequency. Right, figure 1 shows the electromagnetic spectrum. Give the names of parts A and B of the electromagnetic spectrum. So this is just knowing your order of them. So it goes radio, micro, infrared, and then between infrared and ultraviolet, you've got to know it's the visible part of the spectrum, what we actually see, then ultraviolet, X-rays, and then the highest frequency type of wave is your gamma rays. So A is visible, and then B is gamma. Okay, so there are loads of mnemonics out there, but you've just got to make sure you know the order of the electromagnetic waves. Different types of electromagnetic waves have different uses. Draw one line from each type of wave to its use. Okay, so microwaves, whilst yes, they are obviously used in cooking, that's not one of the options here. Microwaves are actually the waves that are used in your phones for communications. So mobile phones use communications, mobile phones use satellites, so satellite communication. Ultraviolet is used in energy efficient lamps, okay, so giving off, like, if you think of various different light sources, uses ultraviolet, checking banknotes, etc., and also UV in like tanning beds, uses UV lamps as well. And for X-rays, obviously we use an X-ray for bone imaging, okay, medical imaging in general. Electric heaters, the type of wave that we use for heat is infrared. So whilst not an option here, electrical heaters are used as infrared heaters. So a student investigated how the surface of the colour of a surface affects the power of the infrared radiation emitted by the surface. So rereading the question, first thing I would do is thinking about your variables from it. So a student investigated how the colour of a surface affects the power of the infrared radiation emitted by the surface. So what I am changing, my independent variable is the colour of the surface, and I'm measuring the amount of infrared radiation emitted, which would be my dependent variable. Figure 2 shows some of the equipment used. So you've got a black matte surface, a shiny white surface, an electric kettle, measuring cylinders, thermometers, and then an infrared detector that shows how much heat infrared is being given off. The infrared detector measures the power of the infrared radiation emitted by the flasks. The student poured hot water into each flask. What should the student do to reduce the risk of burning herself with hot water? So this is a general safety risk assessment question. If you're using hot water, what could you do? You just got to suggest something logical and sufficient. So I would be saying things like, obviously, you'd be standing up, you wouldn't pour boiling water sat down. You could use a funnel. You actually, amazingly, you could get, say, just saying pour it slowly. That would be accepted. And you could also you have to be more specific about this. You can't just say gloves, but you could say wearing heat-proof gloves. That would also be accepted. It then says, describe how the student should use the equipment in figure 2 to compare the power of infrared radiation emitted by each flask. So it's a 4-mark basic planning question. They've given you the equipment and you've got to describe how you could use the infrared detector to determine the power from each surface. Okay, and you should also be thinking about what things you would keep the same, your control variables. Okay, so from this information, I'm just going to jot down some key bullet points, what I would put into that 4-marker here, but I'll jot it on this part of the page. So the first thing I would be doing, well, using the kettle, I would heat the water. So use kettle to heat water. Okay, once I've heated the water, I would then, so that's what I'm using my electric kettle for, what should I probably keep the same? Well, the amount of, I know I'm going to be putting the water into my flasks, but I need to make sure they have the same amount. What am I going to use to do that? My measuring cylinder. So I might measure, and you make up an amount, 50 centimetre cubed of water, of hot water, using measuring cylinder. You would then pour it into each flask. Okay, so you then have got your water set up in each flask, ideally almost at the same time as you can. What you would then do is record the starting temperature, using the thermometers. Okay, what you would then do, so you're ensuring that another control variable is keeping them, or making sure they're at the same starting temperature to begin with. You would then use the infrared detector to record the amount of infrared emitted from each colour. But to keep it the same, you would set the infrared detector at a set distance. So set it at 30 centimetres away from each flask and then record it. But you can then use it to compare the results. So obviously, the highest the value, the higher values means more infrared is emitted. If you had a lower value, you'd have less infrared being emitted. Okay, so you've just got a basic method here, using that piece of equipment to show which one gives off more infrared radiation. It then says, a student investigated how the power of the infrared radiation emitted from a flask changed with time. And it says, describe the pattern shown by the data in table 1. And you've got 2 marks here. So remember, describe just means say what you see. So, as time is going on, what is happening to the power? Well, start off with the obvious mark. As the time goes on, the power is decreasing. So link the variables together. As the time increases, the power decreases. Now that would get you 1 mark. However, does that go at a constant rate? Okay, is that always, if I was drawing a little sketch graph of it, would it be going down in a straight line? Well, this data, you can see, this has a gap of 0.8, this has a gap of 0.7, down here, this has a gap of 0.2. So what I would also then be doing is saying the change, or the rate of the decrease slows down over time. So the rate of power decrease slows over time, and that would get you the second mark. Okay, or every 60 seconds you can see the rate is decreasing, and you could quote some values from it. It's gone from 0.8 to 0.7. Question 2.4. What is the most likely value for the power of the infrared radiation emitted after 480 seconds? So go back to your graph, you're going to 480, and you want to try and spot the pattern. What do we think it would be? 4, 4.2, 4.4, 4.6. Well, we know it's going down, so we've got a gap of 0.3 here, we've got a gap of 0.2 here, so therefore I might predict that I might have a gap of 0.1. And if I had a gap of 0.1 here, that would give me 4.4. So I'd be more inclined to go with 4.4. It's definitely not going to be 4.6 because that is higher and the rate is slowing down, it's getting cooler. And the other two are a bit more of a drop than you might predict. A Leslie cube is used to demonstrate that different surfaces emit different amounts of radiation or emit different amounts of radiation. Figure 3 shows an infrared detector and a Leslie cube filled with hot water. So it's a similar practical, but this time, instead of using different flasks, we've got a Leslie cube that has different surfaces. Give one advantage of using a Leslie cube rather than using the equipment on figure 2 on page 4. Well, if we're using a Leslie cube that we then fill up with water, we know that the water is always going to be exactly the same. Okay, we don't need to worry about the starting temperature because we're using the same water each time. Okay, so I would be going, an advantage is that all the surfaces are exposed to the same temperature of water as it is the same water that's in there on each surface. Okay, yeah, and I would say that's your key advantage. You could also say, because it is the same water, the water does not need to be measured because then it's in the same flask, so it doesn't matter how much water is in there as long as there's enough to record a difference. The teacher improved the demonstration by using 4 infrared detectors connected to the data logger and a computer. Each detector was pointed at a different surface on the Leslie cube. The distance between the surface and the detector was the same in each case. Give 2 reasons why this improved the demonstration. Well, so saying if I've got infrared detectors already set up permanently at each side, why is that better? Okay, why does that improve my investigation? Well, the key things are, if you've got 4 detectors, you don't have to move it. So all measurements, I'll just record these 2 points down here next to the diagram, but all measurements can then be taken at the same time. So that's your first key advantage. And therefore, you can also say, well, you could also say, because they don't moved at the same time, an advantage is there's no need to move it. That is also allowed. And then for your second mark, because you're not having, it will be at exactly the same time, you would say the second point is that it's just more accurate, because you'll be closer to your true value. You're not, you're basically controlling a control variable for time much more accurately. Question number 3 then. Figure 4 shows an apple hanging from a tree. The X marks the centre of mass of the apple. Draw an arrow on figure 4 to represent the weight of the apple. So what we should remember is weight is another word of a force or way of describing the force of gravity. We know gravity goes down from the centre of mass. You don't need to label it, you literally just need to draw that arrow on. It then says the apple has a mass of 0.150 kilograms, has a gravitational field strength of 9.8. Calculate the weight of the apple and it gives you the equation. So you don't need to rearrange it. Your mass is 0.150, gravitational field strength is 9.8. You literally times them together to give you 1.47, and the unit's already given to you, newtons. So the weight on the apple would be 1.47 newtons. The apple in figure 4 is stationary. Why is the apple stationary? Is it because the resultant force of the apple is downwards? Is it because the resultant force is upwards? Or is it because the resultant force is 0? Remember, this phrase resultant force just basically means the overall force acting on an object. Well, if the overall force acting on an apple was downwards, the apple would move downwards. If the overall force was upwards, the apple would move up. But because it's not moving, it's stationary, it means there is no resultant force, so it would be the bottom one. When the apple is ripe, it falls from the tree and it accelerates towards the ground. Why does the apple accelerate? Is it because the resultant force on the apple is downwards, upwards, or 0? Well, it's accelerating downwards, so the resultant force is therefore down. The overall force on the apple is bigger, going down towards the earth, and therefore it accelerates. It says, question 3.5, the acceleration of the apple is 9.8 meters per second squared. The velocity of the apple changes from 0 to 4.9. Calculate the time taken for the apple to hit the ground, and it gives you the equation. So this time we're calculating time taken. And we know that's the change in velocity divided by the acceleration. So my change in my velocity is going from 0 to 4.9. So it's just 4.9. Okay, if it did give you a different number that's not 0, you'd have to calculate the difference. But it's just 4.9 divided by the acceleration, 9.8. If you put that into your calculator, it gives you a time of 0.5 seconds. So it hits the ground in 0.5 seconds. Question number 4 then. Figure 5 shows a compass. Why does the compass always point in the same direction when it's not near to a magnet? So this is the point that compasses always try to point north. Why do they always point north? Well, it's not because the compass itself is magnetic. The compass spins in relation to a magnetic field, and the biggest magnetic field comes from the Earth. We should remember that the Earth has a solid iron core, and it is emitting a magnetic field, around the Earth, coming out of the North Pole, going round to the South Pole. What material could the needle of the compass be made from? So this is testing whether you know your magnetic materials. The only 3 magnetic elements that we've got are iron, nickel, and cobalt. These are the only 3 magnetic elements. However, you can sometimes make steel from a mixture of iron and cobalt. Steel is an alloy, and therefore steel can sometimes still be magnetic. Okay, depends on how much iron you've got in there, but generally steel is still magnetic. Aluminium, copper and plastic are not magnetic elements and therefore wouldn't be attracted to the Earth's magnetic field. Figure 6 shows a coil of wire. There is a current in the coil. The circles show the position of the 4 compasses. Okay, and the question is, which statement describes the magnetic field of the coil? The field has the same strength at all points, it's stronger away from the coil, or the field is strongest at the ends of the coil. Well, the field is stronger when you've got more magnetic field lines close together. So it's not stronger when it is further away from the coil. It's actually magnets, and you should see this if you ever use iron filings in class, all the iron filings stick to the poles. So therefore, you would say the field is strongest at the ends of the coil. Draw one arrow in each circle on figure 6 to show the direction of the magnetic field at that point. So this is again assessing whether you know the direction of a magnetic field. It's given you north and south. You should know that all magnetic fields come out of the north and they loop round to the south pole. Okay, so it comes out of the north, then loops round, and then eventually it will go back in the south. So your arrows need to be facing that way to get the marks. It then says, question 4.5, give 2 ways the magnetic field around the coil could be made stronger. So if I've got an electromagnet, what could I do? There are 3 things you can do. You can increase the current going through the wire. You can increase the number of coils, okay, the number of turns, okay, coils or turns in the wire. And the final thing you could do, you could add an iron core. So this is just an individual coil of wire that is sometimes called a solenoid. So if you've just got a coil, it is called a solenoid. But if you've got a coil of wire with an iron bar in the middle, that is what we then call an electromagnet. Right, question number 5 then. The stopping distance of a car is the sum of the thinking distance and the braking distance. Which factors would affect the thinking distance of a car? So remember, if you've got a stopping distance, it's the amount of distance travelled before a car or an object actually stops. So imagine a car is coming along and then a cat jumps out in the middle of the road and the car slams on the brake. Now the time it takes for the driver to then think about stopping is called the thinking distance. The time it then takes once the brakes have been pushed is called the braking distance, and that together makes the overall stopping distance. So we have been asked what factors affect the thinking distance, and this is specifically really about the driver. So what factors affect the thinking distance of the driver? Well, the condition of the tyres doesn't affect the driver, not either driving on wet roads or the mass of the car. It would be how tired that person is. If they're more tired, they will take a longer time to think about pressing the brakes, or if they were distracted using a mobile phone. Question 5.2, explain why a person should not drink alcohol and then drive. Well, we know if you increase your, if you have alcohol, so alcohol, what does that do to the body? Well, it slows down your reaction times. So it slows down reaction speed. So what I should have said is slows down the reaction speed. So reaction time, the time taken for it to actually affect, increases. So this is a free marker, so we need to expand on it. So as the reaction time increases, the thinking distance increases. And therefore, because the thinking distance is increasing, it is more likely to have a collision. So a person that is driving has slower reaction times, or the reaction time increases. It has a longer thinking distance and therefore more likely to have a collision. Those would be your 3 marks there. The highway code gives information on how thinking distance depends on the speed of a car. Figure 7 shows the information from a graph. What is the speed of the car if the thinking distance is 16 metres? So you have to go to thinking distance in metres and you need to go to 16. Go to 16 and you can see this is quite an easy scale. It's just each little square is worth 1. Go along to your line of best fit and then down, and you can record what value that should be. Now you would do it with a ruler, making sure it's accurate, and if you do it with a ruler, it should land on bang on 23. Okay, there we are. Describe the relationship between speed and thinking distance. 2 marks. So again, describe, say what you see. Everyone should be able to get the easy marks. That you can say, well, 1 mark, as the speed of the car increases, the thinking distance increases. That would get you 1 mark. So as the speed increases, the thinking distance increases. Then, to get the 2nd mark, and this one is quite challenging for a foundation paper, you've got to spot the overall pattern. Now you've got a straight line going straight up from the origin. What that then means, if I pull off some readings, so 10 gives me 7, 20 gives me 14. Okay, so what I can see here is that it's doubling. If I went to 5, I can see it's 3.5. So as your speed is doubling, your thinking distance is doubling. And this relationship has a special word. If one variable doubles, which causes the other one to double, it's called a directly proportional relationship. So as the speed increases, the thinking distance increases. 1 mark. You could then just say it is a directly proportional relationship. Okay, so question 5.6 then. It then says a car accelerates at 5 meters per second squared over a distance of 45 meters. The initial velocity of the car was 0 meters per second. Calculate the final velocity of the car using the physics equation sheet. Give your answer to 2 significant figures. Okay, well, it says straight away, well, using the physics equation sheet, regardless if you get the full equation sheet in the year you do your GCSE, this equation will be one that is provided to you, which is your final velocity squared minus your initial velocity squared equals 2 times the acceleration times by the distance. Okay, so it will be written as, it'll be written out pretty much like that on your equation sheet. You can then just substitute in your numbers. Okay, so people think and look at this equation and think, crikey, this is quite hard. But actually, first of all, if you just substitute in your numbers, that will get you some marks. So your final velocity in here is what you are calculating. So you can just put a question mark. Minus the initial velocity, which was 0 squared, 2 times the acceleration, which is 5, times by the distance, which is 45. Now, if you get to that stage, you get 1 mark just for putting in the numbers. What you can then do is then start to rearrange it, okay, if you need to. Well, first of all, though, if you've got 0 squared is nothing. So therefore, your final velocity squared minus nothing is just the same, equals 2 times by 5 times by 45. Now, if you do that, this side of the equation, that gives you 450. So your final velocity squared is 450. Well, the opposite of squaring something, because we don't want final velocity squared, we will just want final velocity is square rooting it. The opposite of squaring, square root. So if you square root 450, that gives you 21.213, 20343. Now the answer has just set to two significant figures. So you draw your line after two figures and it's 21.2. So therefore it's rounded down. So you don't need any of this. Your final answer would just be 21 meters per second. And that's it. Right, question 6 then. Figure 8 shows a longitudinal wave. What do labels A and B represent on the diagram? So we should recognise that this is longitudinal, so the particles are vibrating left and right as the wave passes across the page. Now, if you've got particles that are closer together, we call it an area of compression. And this is just one of the key words you need to know. If you've got particles that are spaced out, it's called an area of rarefaction. So A, you would just put the word in rarefaction. Just something you need to know. If they're together, it's compression. If they're spaced apart, it's rarefaction. You've then got B, which is the distance between two areas of compression. So in a longitudinal wave, this one would be called the wavelength. Okay, so amplitude is not something you can really show on a longitudinal wave. Reflection, this wave isn't hitting anything, so it's not reflecting. So rarefaction and wavelength are your answers here. The wavelength shown in figure 8 has a frequency of 4 kilohertz. Calculate the period of the wave, use the physics equation sheet and give the unit. So if you look for your wave equation, that is period. The period of a wave, the equation says, is 1 divided by the frequency. Now, the period of a wave is actually saying the time of the wave, or the time period of a wave. So it's basically how long it takes a wave to then pass a certain point, or one complete wave, how long it takes it to pass one certain point. So you've been told the time period is 1 divided by the frequency, so it's just 1 divided by 4 kilohertz. But in this equation, it needs to be in hertz. So kilo is 1,000, so it should be 1 divided by 4,000. If you do 1 divided by 4,000, it equals 0.00025, and because the period is a time, we always measure time in seconds. So it takes 0.00025 seconds in order for this wave to then pass one certain point, and that's it. Okay, it then says, use the physics equation sheet to answer 6.3 and 6.4. Write down the equation that links frequency, wavelength and wave speed. So I look at my equation sheet. If you get it in the exam, if you don't, you might just need to know this one. Wave speed is frequency times by wavelength. It then says a sound wave has a frequency of 300 Hz and it travels through the air. The air has a temperature of 28 degrees. Determine the wavelength of the sound wave using figure 9. So I know I'm going to have to use the graph they've given me. So if I know wave speed is frequency times by wavelength, to get wavelength by itself, so wavelength would be equal to wave speed divided by the frequency. You can put it into a little triangle if you need to. Wave speed, frequency, wavelength. So to calculate my wavelength, wave speed divided by frequency. Now, my wave speed, I don't actually know. It's not given to me in the question. My frequency, though, is 300. To get my wave speed, I need to use my temperature and my graph that it's been given. So I go back to my graph, and I can see here, well, if I go to 28 degrees, I look at this point, I go up, and then I can go across, and it gives me the speed at that particular temperature. So reading on my scale, 3 little squares above 345, so it'd be 348. So what I would then do, substitute in that value, 348 over 300 would give me a wavelength of 1.16 meters. Okay, and that would be my final answer. Last question then, question 7. Figure 10 shows competitors in the wheelchair race at the London Marathon. The distance of the London Marathon is 42,000 metres. Use the physics equation sheet to answer these questions. Write down the equation that links distance, force and work done. So, this is one equation you might need to know if you don't get given the full equation sheet. The work done is force times by distance. During the race, the competitors work against air resistance. The work done against air resistance by the winner of the race was 3,336,000 joules. Calculate the average air resistance acting on the winner during the race. Okay, so it's asking us now to work out what the air resistance is. Now they've just asked us to find that equation above, so we know what is actually basically it's going to be asking us to use that equation. Now, work done, what we need to know, is also a form of energy. So the work done is given to us. So 3,360,000 equals something times by our distance, and we've been told our distance was back on the previous page, which is when it gets a little bit, make sure you read all parts of the question, 42,000 metres. Okay, now we are then calculating the average air resistance, and air resistance is a type of force. So that is 1 mark by getting to that stage. You then rearrange it. Okay, so calculating air resistance, instead of timesing by 4,200, you would do 3,360,000 divided by 42,000 equals our question mark. If you do that, that would then give you an answer of 80 newtons. Then, you're still using the equation sheet to answer 7.3 and 7.4. What is the equation that links distance travelled, speed and time? You'd look at your equation sheet, and you'd find the one that matches it, which is distance equals speed times time. The distance of the London Marathon is 42,000 metres. The winning time for the race was 5,600 seconds. Calculate the average speed of the winner of the race. Okay, so if distance is speed times by time, speed is equal to distance over time. So 42,000 divided by 5,600 would give us 7.5 metres per second. So there are perfectly loads of easier questions towards the end of the paper, so never stop going. It then says, explain why the speed of a competitor might change during a race. Okay, so this is then thinking about as the last question on the paper, but why might the speed of a competitor change during the race? Well, they've left it quite open here. There's loads of different things you could say. Well, you can think about yourself whenever you've done a race. Okay, they would accelerate, you go fast at the start. So the speed increases. However, as time goes on, what happens towards the end of a race? You start to get tired. During or near the end of a race, people get tired and slow down. And then you can think, what other factors might affect the speed? Well, it could be the actual road itself. The course or road is not flat and might change. Going uphill, working against gravitational or gaining gravitational potential energy might slow you down. Will slow competitors down. You could also say that people might sprint at the beginning of a race. You could even say, because they've talked about wheelchairs, people might get a puncture. Okay, and then you could also say, but even potentially about weather conditions. So weather conditions affecting it. So that, basically using some logic, bit of a strange question to be honest at the end of a paper, but there's loads of different things you can say here, just using a bit of common sense, but thinking about how it would affect the speed. Okay, so that is the end of this paper then. And what we can then do, hopefully, if there's anything that jumps out at you, look at the Cognito clips and you can go back over and revise the specific topic that you need to. Hope it's been useful. Many thanks.